All right, here we go, Unit 5, Lesson 6. We're going to be continuing our work with the mean value theorem, and we're going to focus in today on using your calculator to solve AP-style multiple choice and free response questions where you do have access to a calculator and sometimes are required to use one. Now, there's a couple of key points here that I need you to keep in mind that are made a little bit tricky by distance learning. The reason this is tricky is that Desmos is a little bit more powerful than your TI-83. And it's unclear right now what conditions you're going to take the exam under in May. And so I'm waiting to work on TI-83 skills until that becomes clear, but I want to make sure you're still practicing with the same limitations on what your calculator can do. Specifically around derivatives. Your TI-83 calculator, if you have one or use one at school, it can calculate a derivative at a point. It's basically just like estimating the slope using a computer to calculate really close approximations of a tangent line. So if you enter into your y equals in your TI-83, if you enter in y equals 3x squared minus 10, there is a menu option, we'll go over it if you're going to be using them, where you could calculate the derivative at a point. For example, you could calculate f prime of 5. And the calculator would just tell you, oh, that's 20. But what the calculator actually can't do is find general derivatives. If I asked you to find f prime on your own, the way you would do it is you would use the power rule. The 3x squared minus 10x, if we took the derivative, becomes f prime of x equals 6x minus 10. And then you'd plug in 5, you get 30 minus 10, you'd get 20. You cannot use the calculator to find this 6x minus 10. So I guess I should have written those backwards, green versus red. But you can't use the calculator to find general derivatives, only derivatives at a point, even though Desmos can technically do this as well. So everything you see today is going to play by those rules. So let's see exactly how you would solve this problem if you could take derivatives at a point, but not actually graph derivatives unless you find them on your own. So here's a question from the BC exam in 2003, number 92, but it's an AB topic. Let f be the function defined by f of x equals x plus the natural log of x. We've got all these multiple decimal place numbers here to the thousandths place, so that's your clue that this is going to require a calculator. So I'm going to go ahead and type this in, f of x, and I use f of x so that I can plug in easily. You'll see what that looks like in a second. F of x equals x plus the natural log x plus, it's in functions, miscellaneous, the natural log of x. So here's what this function looks like. Let's see what they want us to do with it. What is the value of c for which the instantaneous rate of change of f of x at c? And so if I were to say what this is, the instantaneous rate of change of f at x equals c, that's a lot of words to mean one thing. That means f prime of c is the same as equal to the average rate of change of f over 1 to 4. So the average rate of change on 1 to 4, that's kind of made up notation there, which would of course be f of 4 minus f of 1 over 4 minus 1. Now they're not using the term mean value theorem, and you wouldn't really even need to know that, but this is an application of the mean value theorem that this is guaranteed to exist. All right, so let's look at how you would use Desmos here. The first thing I would do is I would restrict this interval, just so we can really focus in on what we're talking about. I only want to know what is going on where x is between 1 and 4. The way you do that on Desmos, 1 is less than or equal to x is less than or equal to 4. There we go. So we're just talking about this weird little segment right here. It's kind of very slightly concave down, but with a positive first derivative. And so the first thing we need to do is we need to actually calculate this rate of change. And here is where the calculator is super useful. You could technically take out a TI-83 and you could type in 4 plus the natural log of 4, all of that, minus 1 plus the natural log of 4, all of that over 4 minus 1. That is your average rate of change. But Desmos can take care of this for you. And it can take function notation, and so can your TI-83. So you're allowed to do this. You're allowed to just write this all in at once as f of 4 minus f of 1 all over 4 minus 1. And yeah, that seems reasonable, kind of a slightly positive slope there. Here's what I'm going to do. I'm going to assign that a variable, m, meaning slope. M is equal to that number. And just to see visually what this looks like, let's go ahead and graph this as a line here, y equals same variable, right? Desmos is smart, it knows what m means now. And I'm going to do a slider for b, so we can just move this up and down. And so this is the slope of the secant line, and all we need to do is line it up to find the actual equation of the secant line. So maybe we can like zoom in a little bit here, so we can actually try and line this up, give or take, right? That is the slope of the secant line. The average rate of change is 1.462, right? Or that would be enough to write down here. And what the question is asking is, at what point is there a tangent line slope, an instantaneous rate of change, a calculus rate of change that is the same? And if I were to eyeball it, right? If I were to eyeball it by sliding this up, I don't know. Like, it looks like it's going to happen somewhere, give or take, like around here maybe, somewhere in this like 2 and some change range, but not all the way at 2.5. So just by eyeballing it, I think it's going to be either C or D. But here's how you tell for sure. I'm going to show you the way that you can do, I want to show you this just so you know that it is a tool that Desmos has, but I need you to know that you cannot use this because you cannot use it on the calculator. Technically, look what Desmos can do. F, and then let me see if I just have to find this F prime. Maybe I do a shift. Yeah, F prime of X. So Desmos can actually graph a full-on derivative like that. You cannot do that. Your TI calculator cannot do that. So we're not allowed to do that, but it's really just one tiny step. You just need to do it on your own, right? So if we have f of x is equal to x plus the natural log of x, on your AP exam, you would be expected to be able to do this part on your own. F prime of x is 1 plus, right, the derivative of the natural log of x. That's one of those memorizer ones. 1 plus 1 over x. Now we can go ahead and graph that, and I'm just going to call this function g of x, right? The derivative, g of x equals, not absolute value, equals 1 plus 1 over x. And see, it's that exact same graph, but you do have to find it by hand, right? And you want to get in that habit. Okay, now what did we actually want to know? We wanted to know when, and so I'm going to block the rest of these out because these are actually no longer, if you were doing this on your TI, you wouldn't have these. Here is a graph of the derivative. Let's go ahead and let's limit it as well, right? Just so we don't get thrown off. In this case, it doesn't really matter, but sometimes you could accidentally hit the wrong thing here. Let's do 1 is less than x is less than 4. And I want to know, right, this is the derivative. I want to know, when does this derivative equal, this is the instantaneous rate of change, when does it equal that original slope? So all I would have to do here is take either the written down decimal, 1.462, or, just use from the variables y equals m, there it is. So really think about what this is. That red line, y equals 1.462, that is what the secant line slope is. So it's just a flat line. That is what the slope of the secant line is. It's a constant. And then I've graphed the derivative, and I want to know, when does the derivative of f of x equal that instantaneous rate of change? Well, Desmos will help me find that intersection point, 2.164, right there. So the correct answer here is 2.164, and that is something that you could do with your TI calculator as well, all of those steps. As it gets closer to the AP exam, we'll practice like the actual, what you would have to press on the TI to do that. Let's do one more just like really quickly here. I'll rush through this next one just so you can see one that looks exactly like it looks on the Delta Math. Delta Math, I know you're working on your weekly summative assignments, so the Delta Math is literally just one question today. So let's see how we would get through this. All right, we've got our function. We're going to do f of x, same style question here, is equal to x squared minus 4 times the cosine of x. A lot going on there. Oh, cosine of, nope, it was cosine of 3x minus 1. And I want to find all values of x that satisfy the conclusion of the mean value theorem on 0 to 2. So just to kind of lock my mind in here, I'm going to do 0 is less than x is less than or equal to 2. All we care about is this section here. So what I need to do is first I need to calculate the average rate of change. So the average rate of change, again, right, will be f of 2 minus f of 1 all over 2 minus 1. And technically you could do that all out, but it's way easier to just do this on Desmos, and you could do it just like this on your calculator. F of 2 minus f of 1 all over, well, 2 minus 1, I know that's 2. So there's my slope. There's my slope. M equals, oh, not 2 to 1, 0 to 2. Sorry about that. So this should be 0, and this should be 2. Let's clean that up. So this should be a 0, and that should be a 0. All right, so we have, that looks better, a slope of about 2.5. So let's see here. Let's see what happens when we graph this, just to make sure. This is not strictly necessary, but let's just graph this. Y equals, we'll call that M. We'll call this one M. Right? Technically, I could just write that average rate of change right down, but I want to be able to just like see visually what this looks like. So there's my slope. Y equals mx plus b. Just to make sure. Ah, okay. So here's, oh no, that's right. Yep. So there's your average rate of change, right? Or that's the secant line slope. So your average rate of change is about 2.5. And there's actually going to be two answers here, right? Because between these points, it looks like I have an equivalent tangent line slope at something a little bit less than a half. Yeah, something a little bit less than a half, and something a little bit less than 1.5. So we need to investigate where those are. The next step, right? We are sure now that this is our tangent line slope, so I actually don't even need the original function anymore. All I need is this slope right here. All I need is this slope, right? M is equal to, oh no, I did need that. Shoot. Okay, so I do need the f of x because it was using that to calculate it, so I shouldn't have deleted it. I should have just turned it off. So hold on here real quick. F of x equals x squared minus the cosine of 3x minus 1. That was dumb. 4 times the cosine of 3x minus 1. All of that. Oh! F of x equals x squared minus 4 times the cosine of 3x minus 1. And we want to know that just from, again, or I can just, so we have that. We don't need to do that rest part. So, okay, so here we go. Our slope there, our slope of our secant line is 2.5. I just need to know at what points is the derivative equal to that. Now, the issue is, again, when you're using your calculator like this, you have to find these f prime values on your own. So you need to have the derivative rules well memorized to know that the derivative of x squared is 2x using the power rule, and that the derivative of negative 4 times the cosine of 3x minus 1 requires the chain rule. First, it's negative 4 times negative sine of 3x minus 1, right? Because the derivative of cosine is negative sine. Chain rule, right? This is a function inside a function. This 3x minus 1, you have to chain rule it times 3. So what we end up having here is 2x minus, or we'll do this negative 4 times negative 1 times this 3. That would be 2x plus 12 times the sine of 3x minus 1. And so now we can graph this. We can say 2x plus 12 times the sine of 3x minus 1. And we want to know when that is equal to this value here, m. So what I'm going to do is I'm just going to graph y equals m, because that was our slope there. And on the interval 0 to 2, here are our two locations. And so again, you can help yourself just kind of zone in on that. If you want to make sure you're not doing things that are outside of the range you were asked about, you could say 0 is less than x is less than 2. I would have needed that for this derivative. So we'd say 0 is less than or equal to x is less than or equal to 2. And so that's the interval that we care about. One last time, again, what is actually happening here? What is actually happening here is that the purple line represents the secant line slope, like not the slope of the purple line, the value, the y values of the purple line. And so the purple line is located at y equals 2.513, and it has those intersection points at, like I said, a little bit less than a half and a little bit less than 1.5. So on delta math, you would do 0.382. You would hit that little plus sign that's over here, and you would also enter in 1.388, always to the third decimal place.